Okay, we are ready for examples for the related race problems. This is the second part of chapter 4.3. Let me start by the following. A usual well-known type of example. Example 1, let's say. Limit x to the infinity. So evaluate the following limit. We can write at the beginning of the whole example, evaluate the following if limit exists. 1 plus 1 over x power x. Okay, this is a very typical problem that you may already solve this problem by using maybe without L'Hopital, but in this case there is a formula for this type of limits, but we will show it, we will prove it in this example. 1 over x, so if x approach to infinity, then 1 over x will be approaching to 0. So then we have 1 plus 0, we have 1. So then what do we have? 1 power infinity. So then this is of the form 1 power infinity. So in other words, LH cannot be applied in that form. Cannot be applied. But let us do it applicable. We can again do the following. So let's say y be 1 plus 1 over x power x. Then what do we have? If you take ln of both sides, ln y is equal to x times ln 1 plus 1 over x. Then take limit of both sides. We have limit of whenever x approaching to infinity, of course, ln of y will be, so maybe we in the previous part we did a similar example, but we forgot to take limit. Okay, maybe let us go back to our previous example, if you remember. Okay, for that one, and now I see it. Okay, we applied, so we applied here ln y, and you see that we found the limit of at the end of this calculation. So I will go back to our example, but here we have a mistake here, so we have 0. Okay, but this 0 is referred to the following. This 0 is the limit of x to the 0 ln y equal to 0, but I need to evaluate limit of ln of what was the limit of, so y is the function which is given. So let us go back to the question. Okay, it's better to see it again. So this is our y. So y is equal to cosine 3x power 5 over x, but we evaluated limit of ln y. What is the limit of y? So this is the question, in fact. Okay, then this can be written in the following form: ln of limit of x to the 0 y equal to 0. Okay, then this implies if ln of a function equal to 0, then this function must be 1. So then limit of x to the 0 y must be equal to 1, e power 0, which is 1. Okay, this is the result. In fact, this is the result. Okay, if I again go back to the example 1 plus 1 over x power x. Okay, let's check it. Okay, the result of previous example was not equal to 0. Pay attention. It is equal to 1. So now what do I have? Limit of ln y, which is equal to limit of x to the infinity x times ln 1 plus 1 over x. Okay, so if I rewrite this function in the following form, you see that we have infinity times 1 over infinity 0, 1 plus 0, we have 1, infinity times 0. So this is of the form infinity times 0 form. But I can change it by reversing x in the following form: ln 1 plus 1 over x over 1 over x. So what do we get? We get, now we have x to the infinity, of course. So this will be 0. So this will be 0. So this is 0 over 0 form. Okay, now I can apply L'Hopital. Apply LH. What do we get? Limit x to the infinity. So if we apply L'Hopital for ln 1 plus 1 over x, we have minus 1 over x squared over 1 plus 1 over x over the below term 1 minus 1 over x squared. So they will cancel each other, the 1 minus 1 over x squared terms. In the next stage we have x to the infinity. Just I will have 1 over 1 plus, if I have no mistake, 1 over 1 plus x, and this will be equal to, whenever x tends to infinity, we have 1 over infinity 0, so we have 1 over 1 plus 0, which is 1. But this is not the answer, pay attention. Indeed, we have limit of x to the infinity ln of y is equal to 1, which implies that ln of limit x to the infinity y is equal to 1. So ln of a function, if it is equal to 1, so then it means we have limit of x to the infinity y equal to e power 1. Okay. Conclusion. Okay, for this type of problems, now we will have a conclusion. Normally, if you are given a question, so let me say, if we have limit x to the infinity, let me say conclusion here, conclusion, let me write in a better form, limit conclusion, limit x to the infinity 1 plus k over x power x will be equal to e power k. So everything is depending on this k number. If you have a negative sign here, we have to have minus k. Okay, so this is a formula that we can obtain. If you again apply all of this calculation that we did in the above example, you will get e power k. Let us continue. Example 2. We have now another one. Limit x to the 0 sine x over x power 1 over x squared. Okay, this is also a L'Hopital question, but you must pay attention. You have to play with some terms. We have the following. So whenever, if x approach to 0, we know that sine x over x will be approaching to 1. So then we have the inside the parentheses, we have 1. So 1 over x squared will be approaching to what? It will be approaching to infinity. So 1 over 0. Okay, we have then, what do we have? So we have 1 power infinity form. Still, it is not a LH form, but we can play with some terms to get LH form. Okay, let's do the following. Let y to be sine x over x power 1 over x squared, which implies that ln y is equal to 1 over x squared ln of sine x over x. Take limit of both sides. Take limit of both sides will give us limit of ln y as x approach to infinity, sorry, so 0, we have 0 case in this form, in this question, will be equal to limit of x to the 0 ln sine x over x over x. So let us check what form we have. Whenever x is approaching to 0, the below term is 0, the above term, so ln sine x over x will be 1, approaching to 1, so ln 1 is 0, 0 over 0, so this is of the form 0 over 0. Okay, so it means we can apply L'Hopital, LH. Directly, I do direct calculation, limit x to 0, ln of sine x over x, take derivative of the inside function, sine x over x, so derivative of first one, cosine x times x, minus derivative of x is 1 times sine x over x squared, and over itself sine x over x. Pay attention. Okay, here we have several over term, and over maybe we can change the limit x0. It is better to write limit here, limit x to 0. Then the below term, the derivative of we have x squared here. Sorry, maybe I forgot to take this x squared. And derivative of x squared is 2x. Okay, if I rewrite this limit again, as you see, we have here x squared over x. One of them will cancel each other with that one and that one, and the other x will be cancelling by. Can you see it? Or so let me rewrite it. Okay, let me write it better. It's better to, sorry, let's use the right color. 0, so x cosine x minus sine x over x times sine x over do we have a mistake here? X cancel, x times sine x, no, it's okay, over 2x. So it means I have 2x squared. 2x squared sine x here. 2x squared sine x. Okay, let's see if I have a mistake or not. Okay, let us continue. We have maybe it is better to write this as x sine x times 1 over x. Okay, 2x sine x. They are equivalent. Then what do we have? Can we no, it doesn't make sense. Okay, writing 2x it doesn't make sense, so maybe it is, we can keep it 2 times x squared. So now if you put x is 0, what do we have? 0 minus 0, 0, so it is again 0 over 0 form. Okay, it is better to apply one more time L'Hopital. Apply again L'Hopital. Limit x to 0, derivative of the above term, derivative of x times cosine 1 times cosine minus x times sine, derivative of second one times first one, minus cosine x over, so the derivative of 2x squared, let's say 4x times sine x plus 2x squared cosine x. So these cosine x's cancel each other here, and one of the x's we may cancel each other with that one. After that stage we will have limit x to 0. Maybe we have a result, or otherwise we have to do one more step. Minus sine x over 4 sine x plus 2x cosine x. So as you see, if you put 0, again we have 0 over 0 form. It means I have to apply one more time L'Hopital. So this is a good example in order to see how L'Hopital works in many stages. Okay, if you have many times L'Hopital rule, still there is no problem, you can apply. So derivative of sine is cosine x over, pay attention to the sign. So we have 4 sine x is 4 cosine x plus 2, derivative of 2x is 2 times cosine x plus derivative of cosine is minus sine x times 2x. Okay, now if I put again 0, this will be 1, this will be 1, and this will be 0. What do we get? We get the following: minus 1 over 4 plus 2, which is minus 1 over 6. Okay, we get the result. Nice. But this is the result of the following. This is limit x to the 0 ln y is equal to minus 1 over 6, which implies that then limit of x to the 0 y will be e power minus 1 over 6. Please don't forget to each time when you apply ln of function y, you must pay attention to the last stage. You must change it to limit y. Okay, let's see if I have more questions about L'Hopital rule. Question 2, question 3, example 3. Okay, let's do the following. Okay. far as I remember, I remember that I had some more examples, but okay, let's see this one. This is easy. Limit x to 0, 3 power x minus 1 over x. This is an easy question, in fact. Indeed, this is the definition of derivative. Directly you can use the derivative, definition of derivative, but let us use the L'Hopital to make life easy for us. Okay. So this is of the form, if you put 0, we have 3 power 0, 1, 1 minus 1, 0, so it is 0 over 0 form. And obviously, as you see, if you apply L'Hopital, then you get limit x to 0, derivative of 3 power x. This is something you know, ln 3 times 3 power x, over derivative of x is 1. So then if you put 0, we have 3 times ln 3. No, sorry, 3 power 0 is 1. So then I have just ln 3. Otherwise, you must use the definition of derivative. If you let the function f to be, if f of x, let me write an alternative solution, 3 power x, and use the definition. Okay, we can say f prime 0 is equal to limit x to 0 f of x minus f0 over x minus 0, which is x. So so it will be of the form limit x to 0, 3 power x minus 1 over x, and this is the same as taking derivative of f at point 0, so it is ln 3. Okay, we have, if you take derivative of f of x, which is 3 power x. But the L'Hopital solution is much more easier than the given one. Okay, example number 4. Of course, you can find several examples in your book or in previous year exam question or in any book, calculus book. I suggest you to solve more type of example. Evaluate the following limit x to the 1, x power x minus 1 over x minus 1, if limit exists. Okay, if you look at the limit, we have 1 power 1 is 1. Okay, it is not a infinity, 1 power infinity question. So 1 minus 1 is 0, 0 over 0, 0. So this is 0 over 0 form. It means you can apply, of course, L'Hopital rule. Okay, after applying L'Hopital rule by LH. But in this case, so let me just say a note here, then we can apply L'Hopital. If you let y be x power x minus 1, then we have x power x will be what? Y plus 1. Okay, then take the limit of both sides. Take the limit of both sides. What do we get? We get the following. We have x times ln x. Take the ln of both sides. I'm sorry. Please correct it. Take the ln of both sides. ln y plus 1. Okay, ln y plus 1 equal to x times ln x. So if we differentiating both sides. Okay, this is not an only way to solve this question. Differentiating both sides. This is just one of the solutions that I can do, so you can apply other way to find a solution. If you differentiate x ln x, so derivative of x is 1 ln x plus 1 over x times x, we have 1 equal to y prime over y plus 1. Then my purpose is in fact to find y prime. Y prime is equal to y plus 1 times ln x plus 1. So why I did this calculation, I need y prime in fact. So you will see now why I need y prime. So now go back to question, limit x to 1. We had y over x minus 1. So this is of the form 0 over 0, so we can apply L'Hopital. So then limit x to the 1 will be y prime over derivative of x is 1. In other words, I evaluated y prime in order to calculate this limit. Okay, so now you can just, instead of y prime, you can write directly limit x to the 1 y plus 1 ln x plus 1 over 1, of course. Then what's my y? So y was equal to directly x power x minus 1. So limit, substitute instead of y plus 1, you can write x power x. Okay, just x power x. Okay, go to the expression here. You can verify that it is true. So y plus 1 is equal to x power x. Okay, one more step, times ln x plus 1. Now put x is 1, 1 power 1 1. So then ln 1 is 0, 0 plus 1. The answer is 1. Yeah, it's nice. It is a nice answer, but that's it. In fact, the question was not difficult, as you see. This was question number 4. Question number 5. Okay, let's evaluate again. Limit x to the 0 secant x minus 1 over x squared, if limit exists. If you put 0 secant x cosine 1 over cosine, which is 1, 1 minus 1, 0, 0 over 0 form. Okay, apply L'Hopital. Limit x to 0, secant x, derivative of secant x is secant x times tangent x, don't forget it, it's important, over 2x. Okay, we have indeed 0 over 0 form again, but can we cancel some terms? Secant x is 1 over cosine, tangent x is sine x over cosine, so it's better to maybe apply one more time L'Hopital. Okay. We can do it, of course, you can continue your calculation because we have sine x over x somewhere here. Yeah, maybe it's better. So let me write it again. Not using L'Hopital. I think I can get some better form than L'Hopital. Secant x is 1 over cosine x. Tangent x is sine x over cosine x. Let's say 1 over cosine x times sine x, and we have 2x. Okay, sine x over cosine x here. This makes sense for us. This is 1. Limit x to the 0. This is 1. So we have 1 over 2. Cosine x is, this is 1, again 1. So the result will be 1 times 1 times 1 over 2. So it is 1 over 2. Or you can apply again L'Hopital rule in the previous stage. Let's see if I have a better question, an easy question I'm searching for. Or maybe a type of question that we didn't apply. Okay, let us do more of that one. Maybe this is also not bad. Limit x to the point 1 ln x over x squared minus 1. Okay, this question is also okay, why I'm here. Okay, there is a mistake here. Maybe we can erase this form. Okay, we have now, this is of the form ln 1 is 0, 0 over 0 form. Apply L'Hopital directly. Limit x to the 1, derivative of ln x 1 over x, derivative of x squared is 2x minus 0. So then I have limit x to the point 1, 1 over 2x squared, which means we have 1 over 2. Not a difficult question. Okay, maybe we can do that one. Okay, example number 7. Limit x to the 0 tangent x power x. Okay, we did a similar one, but we didn't do 0 power 0 form. Tangent x at point 0 is 0, power 0, this is 0 power 0 form. This is the first example of 0 power 0 form. Okay, we can in fact apply either y is equal to ln x, if you remember, y is equal to tangent x power x, or you can use directly e power, writing e power, but I'm preferring to use let y is equal to tangent x power x, then you will have ln y will be x times ln tangent x. Then I can take the limit of both sides to continue. Limit x to the 0 ln of y will be equal to limit x to the 0 ln of tangent x times x. But still here we have a problem, because when you look at this limit, this is 0 times tangent x is 0 ln 0 minus infinity, so it is not of the LH form, but I can change it to LH form in the following. We can rewrite it as limit x to 0 ln of tangent x over 1 over x. Okay, now it makes sense. This is now of the form minus infinity over infinity, or infinity over infinity, doesn't matter. Okay, then apply L'Hopital. Limit x to 0, derivative of tangent, which was secant square x. If I do it, okay, let me do it. Secant square x over itself, tangent x, over minus 1 over x square. Let's see if we can find some result from here. Limit x to 0, second is 1 over cosine square x over sine x over cosine, or cosine x over sine, over minus 1 over x square. So one of this cosine term cancel each other here. We have limit x to 0, then I have 1 over cosine x times sine x minus at the beginning and x square above. Okay, we see it maybe in this form, limit x to 0 minus x over cosine x times x over sine x. So the second term here, this limit will be 1, approaching 1 whenever x approaches to 0, and cosine 0 is 1, but this is 0, this is approaching to 0, so the result will be 0. But this is not the result, in fact, this is the limit of ln of the function. Limit of x to 0 ln of y equal to 0 implies that limit of x to 0 y is our function, the original one, e power 0, which is 1. The result is 1 indeed. Okay, maybe a last example, then we can stop, and you can solve more examples by yourself. Example 7, example 8. One example, maybe this may be of the following form. Limit x to the 0 right hand side 1 over x minus 1 over x times e power x. Evaluate that limit. Whenever x is approaching to 0 from right hand side, put 0 in the function. We have 1 over 0 infinity, 1 over 0 infinity, so infinity minus infinity form. Again, this is an indeterminate form, but you have to change it to in order to make sense, you must use LH. So let us rewrite it. This limit is equal to limit, so make the denominators equal, x to the 0, which means, okay, we have, if you multiply by e power x, so we will have e power x minus 1 over x e power x, and this is of the form 0 over 0. Now I can apply L'Hopital, LH. So limit x to the 0 from right side, e power x, derivative of it with respect to x is e power x again. In below term, derivative of first one is x, second one x 1 times e power x plus x times e power x. So if you put 0, it will give us the result e power 0 over e power 0 plus 0, which is 1. The result is again. So maybe I can stop here, and these are so these examples are sufficient in my opinion, but if you try to solve more examples, you will have a more practice, so it will be better for you. So have a nice day.